Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
His group has been working on a lot of things that are quite related to the work that is going on in MSR, doing model checking with abstraction. But they do a lot of work with SAT solvers instead of BDDs. And we are happy that Michael is taking the time to visit here and explain what his group is doing. Without any further ado, Michael.
Thank you very much for the introduction. Is the mic on? It is, OK. I'm very honored to have the opportunity to come here today and to share some of our results that we've been working on in the approximately last 18 to 24 months. So I'll be talking, my presentation is about 45 slides. And if anybody has, other obligations to leave early, I understand. But I'll try to fit everything in 1 hour. But if I do take a few minutes over time, I'll just let you know in advance. I have about 45 slides. So before I go to the next slide, I should go to the final slide. Any work would not be as useful without good graduate students. So I want to recognize the graduate students that contributed to this work. And some of them have graduated, but 3 of them are still working with me. So going back, OK? So then why are we doing this work? Well, we know that today, Boolean programs, or BPs, have been obtained successfully by doing predicate abstraction. And furthermore, in recent years, people look at, OK, even in this Boolean program, it's still very big. And people have been toying around with, OK, there are a lot of local variables. And most of these variables are dormant when you go from one global state to the next global state. So maybe you could do things of that nature. But in any case, whether you do that or not, model checking of these Boolean programs is a severe bottleneck. The time complexity is just exponential. And given a Boolean program, how do you actually go about viewing the control flow graph of this Boolean program? And different approaches have been done. You can view these CFGs as explicit transition diagrams or implicitly. And if you do it implicitly, you can use symbolic methods to go about traversing the CFG. Okay? And for the rest of this talk, we will be concentrating on implicit traversal instead of explicit traversal. Now, also in recent years, SAT has caught a lot of attention in the research community. Okay? Not to say that BDDs are not nice. BDDs are nice, but just so far, BDDs have not been shown to be successful in scaling to large designs. So SAT has shown to be an alternative to BDD-based designs. However, SAT, in the last 45 years or so, have been mostly targeted at solving one solution really fast. Give me a satisfying assignment to a Boolean formula. Okay? Whether you can arrive at a satisfying assignment or show that this is unset. And a lot of advances have been made, especially in the last 10, 15 years. But if we want to use SAT for implicit model checking of these CFGs abstracted from your concrete program, then we have to extend SAT to solving for all solutions. And I'll say more of why we need to do that in a little bit. And to do that, just like in single solution SAT, learning is critical. How do you learn so that you can obtain all solutions? Okay, so for our purpose, we want to extend satisfiability with SAT solver to be able to enable us to traverse CFGs with any finite transition systems implicitly, symbolically. So this is the outline for the rest of the talk. First, I'll give some background introduction. I assume that most of the audience here will already know that, but in case there's some ambiguity, I'll try to clarify certain things there. And then I'll talk about problems with existing methods. Then I'll go into the meat of our talk, which is we call success-driven SAT. And for this part, we're using SAT to do backward symbolic traversal. Okay? Then we also recently extended to forward traversal. So this is pre-image computation. You can also do image computation. I'll also talk about these terminologies in a little bit. And then I'll show experimental results and draw some conclusions. Software characteristics, I just want to have one slide overview of what our target problem is. Now we know that software, to model check software, is a lot harder than model checking hardware. And one key characteristic that makes model checking software so difficult is that software, generally speaking, have a lot more variables than hardware. Okay? And there are other things like pointers, etc. But here, for the sake of our discussion, we're not going to touch those. Just look at the problem size as our target problem. Now, in recent years, people have tried to exploit the notion of local variables. Okay? Of course, there are global variables, but for most functions, there are local variables, but they still map to the state traversal space. However, if you look at one global state to the next global state, at any given time, if that function is not being touched, all those variables are not of interest to us. And they could be abstracted away. Okay? And that will result in a much smaller abstracted program. And if you do that, then today's hardware-based model checking methods may become applicable. In particular, symbolic methods, not explicit methods. I mean, explicit methods also apply. Okay? But what I'm talking about is symbolic methods might be of great potential. So what is this problem of model checking? Well, given a finite transition system, you want to know whether certain, starting from a initial state, whether you can reach a particular state, say S6. Okay, most model checking problems can be reduced to a state traversal problem. You want to know whether from a starting state of your program, whether you can reach a certain state that something bad happens. You're going after some bug, for example. Okay, where you can map a true property to a false property by negating it, and you want to know that whether that could be done, and that is often done in bounded model checking. Given a finite transition system, you can often view this implicitly as a finite state machine that is constructible through a sequential circuit. Okay, so this transformation is relatively easy. Okay, you can give this explicit description to any of the hardware description languages. So you can build this circuit really, really nicely. Maybe not optimized, but you know that the number of states here is exponential to the number of flip-flops in the sequential circuit. For example, the circuit with 100 flip-flops, you can represent 2 to the 100 states. Okay, so that's these two. I'm going to use these two synonymously to illustrate finite transition system. So when you're talking about model checking, you say, okay, is S6 reachable from S0? Of course, we can do explicit methods. Starting from S0, you can do depth first search or breadth first search until you reach S6, or if you have a notion of fixed point, you've reached every possible reachable state, and S6 is not reachable, then you can conclude that S6 is not reachable. However, explicit methods generally do not scale well to large state transition diagrams. Okay, so symbolic methods are preferred because instead of doing depth first search or breadth first search where you reach one state at a time, you visit one state at a time, you want to traverse sets of states at a time. For example, the notion of an image the image of a state or a set of states is the set of states that are reachable from that starting set. So if the initial state is S0, then the image of S0 is simply S1, S2. Okay? And then you can do the next step. The image of S1, S2 will be S4, S3, and S5. Okay? And you can do that until you have reached every possible reachable states. Now, preimage is just opposite. For example, preimage of S6 is the set of states that you could have come from in one step. So the preimage of S6 is S3, S5. Okay? So traditionally, symbolic traversal have been done using BDDs. So given a finite transition system, you can represent the transition relation of your state machine, if you will, your automata, by this T. This capital T is the transition relation of your finite automata. And then suppose the set of the current states is represented as P of Y, which is also a Boolean function. Then by essentially quantifying the present states and the input variables, you will get the set of states that you could have come from. This is the preimage computation. It's a standard, and this has been successful, for example, in SMV and other symbolic model checkers like that. Okay. Now, as we know, BDDs are extremely sensitive to the variable order. So obtaining the right variable order so that this capital T is even representable is extremely important. Otherwise, the transition relation can explode, and that is often called the memory explosion problem, okay, or space explosion problem. And even worse, even if T is constructible, even if you can arrive at a T, during extensional quantification, because extensional quantification, Y of T is nothing but T when Y is true or T when Y is false. Okay? So you word these together. During extensional quantification, this BDD can explode. Even if the final preimage may be representable, in the process of quantifying, it may actually explode this BDD. So there's a number of problems with BDDs. And so we want to solve this problem. So I mentioned this space explosion problem. Now SAT, as we know, also works on Boolean problems like BDDs. And SAT essentially, in a nutshell, if you look at it from a high level, it solves the same kind of problems. It tries to trade off time with space. So BDD says, given infinite space, I can solve this problem. SAT says, given infinite time, I can solve this problem. Right? It doesn't use as much space. And it has been shown to be successful in bounded model checking. And in the last 2.5, 3 years, is about this using SAT for unbounded model checking to compute preimage and image. And the first one that we know of that was published is by Ken McMillan in CAV 2002, where he successfully proposed a method using SAT to compute the preimage. Okay, we have results to compare our work with that. And then about half a year later, 8 months later, our first success-driven learning-based preimage computation was published in Date, 2003. And then also another group from Korea was extending McMillan's method. Actually, it's pretty much the same, except that they try to compress the set of solutions using SIS. That's a standard two-level optimization hardware, min-term optimization program to minimize that. And then we also extended our work in the following year's Date, and then the image computation this year. But the first step is, can we use, basically to be able to solve this unbounded model checking problem with SAT, the first question we have to ask, or to answer, is how can we use a SAT engine to efficiently perform state traversal? So we want to do some comparison and contrast. Okay, BDD captures all solutions substantially. So in other words, if it has infinite space, it can do it. conventional SAT solvers find one solution at a time. So the most naive strategy that we did, we started out, the student looks at this and says, okay, just use ZChef or something like that, or Berkman, finds one solution, and then say, okay, don't stop, just backtrack. Okay, essentially, that's the method in Macmillan's method as well, except he does some learning right before he backtracks. And I'll talk about that in a little bit. So if you do this in the naive strategy, you enumerate all solutions by enforcing backtracks after each solution is found. This will give you all solutions. But like I said, it trades time with space. This will finish if you have infinite exponential time. So the problem is, in general, there will be a lot of solutions. So we have a solution explosion, and this solution explosion will manifest itself in two problems. One is time explosion, as I mentioned. If you have 1 billion solutions, even if you can find one solution per microsecond, you need to multiply 1 microsecond by 1 billion. And how are you going to store these? If you store these linearly, you'll cause a space explosion like the BDDs had. So I want to give an example. Before when I use just generic Boolean formulas, that usually causes more confusion, I think. We know that Boolean formulas are nothing but a Boolean function, and a Boolean function or functions can be represented like a circuit. So I think this probably will illustrate better, because instead of giving you a formula here, I'll give you a circuit representation. Suppose we want to satisfy this is the output of this gate, z equal to 1. And we say, okay, you give this problem to a standard SAT solver, and it says, okay, give me a solution at the inputs, A, B, C, D, such that z will be equal to 1. And how would it do it? I mean, there are different approaches, but I'll give a very simple approach. Suppose I limit myself to making decisions only at the inputs, because this makes sense. If you make inputs here, you will have the maximum implication power from a SAT perspective, because ZChef does the same thing as well. First, it reads in the CNF formula. It will rank order the variables according to their decision power or implication power, and then in doing so, you will make the inputs as decisions that you should make earlier, because it has the most implication power. So you say, okay, d equal to 1. Let's say the left branch is the variable equal to 1. And then you do BCP, Boolean constraint propagation, and see what other variables are implied, etc., and see if your objective is satisfied. If it's not, you continue, etc. And here, what I show here in braces is what we call the search state, the frontier of gates for which the values are specified. So in this case, G is equal to 1, and that's it. Nothing else is specified. Everything behind G can be specified or unspecified, but definitely nothing after to the right of G is currently specified. So the SAT solver will go and make another decision. Let's say B equal to 0 in this case. B equal to 0 will imply F equal to 1. F equal to 1 implies nothing on H. Okay? So now the search state will be G, as illustrated by this curve, by this dash curve. Okay? Again, this objective is not satisfied yet. So you will continue to search. And then eventually you find a solution. And the solution is D equal to 1, B equal to 0, A equal to 1. And that will give you objective Z equal to 1. Okay? So this is what a standard SAT solver would do. Now, as far as single solution SAT is concerned, it's done. It will give you this assignment along with some internal E equal to 1, F equal to 1, etc. That's the satisfying assignment to this problem. However, if you're interested in finding all solutions to Z equal to 1, okay, what do we need to do? We need to backtrack on A and continue to search. And we find out there is no solution here. It causes conflict, and continue with B, etc., until this decision tree is completely filled. Okay, this is a naive strategy. Now, okay, just a little theoretical discussion on finding all solutions. And this problem has been interesting to the SAT community for a long time. And in 1996, from University of Illinois, there's a new term called Sharpie complete. It says finding all solutions in the SAT instance is called Sharpie complete. I mean, it's not proposing a new class of complexity. It still belongs to NP complete. It just says that given two problems, which both are NP complete, you can still be able to measure them, weigh them, and say that one is harder than the other. Even though both have exponential complexity, some problems are intrinsically harder. For example, this is a very good example. Counting the number of cycles in the graph is harder than detecting if the cycle exists in a graph, okay? Because the number of cycles could be exponential. So counting them one by one, suppose finding a solution in the problem is already exponential complexity, and then to count the number, and if the number is also exponential, then you have sort of a double exponential, if you will. So he calls this class a Sharpie complete. Okay, so let's contrast. I mean, to look at what are our problems here. Too many solutions will cause time explosion, so we need new ways of learning. Okay, so we don't do this in a naive way to search the SAT decision tree and to explore the complete tree. Storing these solutions linearly will cause space explosion, so we need to store these in a graphical manner. Okay, not necessarily a BDD, but some graphical manner, so you don't store them linearly. Now I want to talk a little bit about Macmillan's method and also the South Korean Kang's method. What they do is every time you get a solution, you generate a conflict clause related to that solution and continue to search. In other words, you want to prevent the future search to re-explore that previously explored space. That's what conflict-driven learning in SAT is all about. So suppose you have two solutions, illustrated here. So suppose this whole thing is a solution space. Yeah.
Another question. I just wanted to confirm this. So it seems to me that the fundamental operation you're trying to implement is existential quantification inside the SAT solver.
Yes.
And that is what you were trying to use represent all solutions for, right?
Yes. That's right. That's correct. And then, but you're extensively quantifying not just one variable, all the input variables of a sequential circuit that represents a finite state machine, right? So if I may go back, this is a very important point. Okay, so as I mentioned here, the image of S0 is S1, S2. The preimage of S6 is S3, S5, S7, right? So the image given a set of states, say 1x, 1, 1, x, x meaning don't care. Okay, you want to find all the states that you can reach here. So you want to find all solutions that can satisfy a given starting state. And preimage would be the same. Given a state or a set of states here, find me all possible solutions that will satisfy the next state. So that's the image and preimage. So that's why, yes, you're solving the extensional quantification, but in the SAT, it's also all solutions problem. Okay, so what the conventional method does is every time you find a solution, it needs to backtrack, right? But before you backtrack, you want to add more knowledge into the SAT instance and say that when you look for solution number 2, keep in mind that solution number 1 has been found. And how can we use that knowledge of solution number 1 to help us avoid certain things? So what it does is, okay, suppose I say, okay, this is solution number 1, and I make this into a conflict space. So in conflict-driven learning, every time a conflict clause is added, suppose A or B, the clause A or B is added, then whenever in the future, if both A and B are equal to 0, you will immediately backtrack because this clause, the new clause that you just added, A or B, evaluates to 0 because when both are 0. 0 or 0 becomes 0, and then you must backtrack, because to satisfy a Boolean formula, CNN formula, every clause has to be set. So that constrains the search space. So what it does is, if I just make this a complete conflict space, it actually will chop solution 2 up, because it says, okay, don't search this space again. Okay, so it will chop it up. So what Macmillan does is it does some abstraction, reduction on solution 1. So it reduces the space constrained by solution 1 to something smaller, a smaller circle, if you will, so that the chopping up of solution 2 won't be as severe. Now, making solution 1 a conflict space is perfect if no other solution overlaps with it. Because this is, okay, in the future search, you don't need to search this space again. Just avoid it. However, in a SAT problem, many, many, many solutions overlap. That's what we'll show. Too many solutions overlap. Therefore, instead of calling this a conflict clause, they call it a blocking clause. They call that blocking just to differentiate between conflict clause and conflict-driven learning and the conflict clause generated by a solution. They call this a blocking clause. So they did this, and also the South Korean people, they also did it this way. But essentially, if there are solutions that overlap it with it, it's going to chop it up like that. So we want to approach this in a different approach, because we saw the problem faced by the previous method. Now, suppose this is our formula, and we want to find all solutions. In the image, basically, you want to find the range, the possible range values. For pre-image, you want to find the valid domain values. We know that any Boolean function, especially Boolean functions that map to a circuit, okay, like a finite state machine, finite transition system, that is a many-to-one mapping. That's given. Different domain values can map to the same range value. We know that. That's what is called a function. Okay? That's what we learned in junior high. So, at any given point, suppose I say, okay, there's a frontier of values 10101, for example. Then there can potentially exist multiple input assignments here that will give you the same value here, because the Boolean function is nothing but a many-to-one mapping. So we want to take advantage of that. And we call this, remember before, we call this a search state. So we want to basically store this search state, or sometimes we call them cusets, as a hash table, and then reuse this as much as we can. So here's the example. So the first thing we did is, okay, given a problem, and we want to find all solutions. So we drew out the decision tree for this particular instance. And the notation is that red square means conflict, no solution there. A green square means there's a satisfying solution there. So the SAT solver continues to search and finds one solution here. Okay? And then we do it in a naive way. So you must backtrack and find another solution. Backtrack, and no solution there, and you backtrack to try this branch, solution, etc. Okay?
So green square means that
solution. It's a satisfying solution.
That is not, I mean, that there exists a solution downstream somewhere? I mean, what does it mean? Like, if 139 is already a solution, then why did you go to 9?
Okay. Well, remember in SAT solver, it picks a variable and the value assigned to that variable. So let's say that 139, the value assigned to 139 was 0, so he takes the right range. So he hasn't found the solution yet. So let's suppose the first solution is found here. I'm just making that assumption. So once you find the solution, the naive strategy is okay, backtrack, don't stop, continue to search, etc. So this is a complete tree. Now, the bars, whether it's yellow bar or the sort of turquoise bar, means that the entire subtree are identical. In other words, this decision tree is actually much bigger than what is shown here. This bar starting with 149, this entire subtree is exactly the same as this subtree with this 149. Okay? Same thing here, same thing here. And here, these two yellow bars, they're identical if you look at their structure. And this validates the fact that a lot of solutions overlap. For example, one solution is 5 equal to 0, 6 equal to 0, 149 equal to 0, variable 108 equal to 0, 107 equal to 0, 93 equal to 1, 139 equal to 0. That's one solution. This solution, see, all these assignments are similar, except for 139 now is equal to 1 instead of 0, and 9 is equal to 0. So these are all possible solutions that will satisfy this instance. Okay? And we're interested in finding all solutions. So how can we use this knowledge that a lot of subtrees are similar to be able to allow us to avoid exploring all these subspaces? If we know that this is the same, if we get to here, we know that this subtree is going to be the same as this subtree, which we will be able to say, okay, stop. Backtrack and explore other branches. Just link these together somehow. And let me see. Okay. Oh, before I go there, I want to just reemphasize this point again, that because this is a many-to-one mapping, the equivalent search states, if they have the same search state, then the remaining assignments left over to justify your objective will also be the same. In other words, their search subtrees will be identical. In other words, the search state obtained here and the search state obtained here must be identical, or their subtree will be different. That means whatever is assigned to your current formula right now leaves the remaining unset clauses, the way the unset clauses are represented are identical, so they have the identical solution space. I hope that is clear. In other words, whenever you make decisions at any given point in time, the unset clauses form a search state. If the unset clauses here and the unset clauses here are the same, then their decision subspace will be identical. Yeah.
It seems to me like this would be the motivation why Brian came up with BDDs. In the sense that if two portions of the subtree are identical, you just merge them and you then get a DAG.
Exactly.
BDDs.
Exactly.
So,
but this is not ordered. The variable order is not restricted. Okay, so this is yes, I agree that decision tree, just like in SAT, a decision tree is nothing but a BDD in a restricted sense. Okay, it's not a real BDD because the way that it picks variables in this branch and the way that it picks the variables in this branch may be totally different. Yeah.
People, they have come up with all kinds of different BDDs. They have relaxed orderings on BDDs and come up with all kinds of decision diagrams.
Yes.
So I'm just curious, are you going to end up with some kind of decision diagram which is not necessarily as restricted as a BDD?
That's right. In fact, that's what we're trying to do. However, the most general, order BDDs are the ones currently that have operations available for them. For example, you can do Boolean operators, you can do other things with them if they're order BDDs. If they're not order BDDs, currently there are no existing methods that can manipulate just random BDDs.
Just a quick comment. I think there are free BDDs that can be used to represent.
Yes. A decision diagram is nothing but a free.
Yeah.
So this is nothing but a free BDD. But given two free BDDs, F1, another free BDD F2, and you say I want to order these together. Currently, there are no methods that can order these together. You must first convert F1 to an order BDD, F2 to an order BDD with the same order, and then you can do operation on them. And not only that, free BDDs are much more compact than order BDDs. That's why if you want to do, that's why when I was talking about before the transition relation, etc., the transition relation may explode because you restrict a particular order. So finding a variable order is extremely important. Okay, free BDD, you don't care about the order. So we're trying to solve this using free BDDs, yes, but through SAT, because the decision tree for all solutions obtained by SAT is nothing but a free BDD. This is detailed stuff. This is basic implementation. I think I'll skip this because there are other ways to. And I apologize for this. I think when I copy slides from one file to another, nothing against Microsoft PowerPoint, but sometimes this does happen. So when both branches of a node have been completed, then we add that to our BDD, or our decision graph. And each time both branches are done, you keep adding. And these counters say how many solutions are underneath. So here's one solution here. There are no solutions here, so it's 0. And then this branch, this number of solutions is nothing but the sum of these two counters. Okay, so here is 1 plus 1 or 2. And every time both sides have been explored, you just pop it up, etc. And here, when we get to here, remember, the search state here, we have a very fast way because we're making decisions from left to right in the circuit view, right? So that they map to the same set. You don't need to compare all the remaining unset clauses to see if they're the same, because that would be too expensive. All you need to check is the cut, the search state, the frontier. If the two frontiers are identical, then their solution subspace will be identical. And we found that this search state and this search state are the same, so you just basically link them together. This is nothing but before, this is a tree. This is a graph, no longer a tree. So when you keep on doing that, again, this is the same as this, so that you can link them together. And at the end, there are 24 solutions. And this is nothing but a free BDD. And this is guaranteed to be reduced also. And the counting problem is solved. Now, we're not saying we'll solve this NP complete. This is still NP complete because finding even one solution is NP complete. We know that. Okay. So, but if we can find all solutions, we can count the number of solutions. Okay, using this very nice.
So the difference between a free BDD and RO BDD is that the path, there's no ordering along the paths.
The variable along one path and the variable along another path may be different. So let's look at standard SAT solvers. Okay, in this all of them, there's a SAT Zoo. That's the most mini SAT. But the most recent ones, GChaF, Grass, Berkman, Sato, etc. What they want to do is they want to find one solution, and they stop when you have found one solution. We need to find all solutions. They use what is known as conflict-driven learning. You learn from mistakes. And what we say is we learn from successes or solutions. Non-representation, conflict causes, ours is equivalent search state, that yellow bar, green bar, etc. And they use this knowledge to enable you to backtrack earlier, similarly. So we can finish all solutions as fast as early as possible. Now I want to give a very simple example why our technique we think is much more superior than existing techniques. Suppose you have two solutions, okay? A, B, C, D, X, Y, C, D. In Macmillan's and the South Koreans method, they have to find these two explicitly. You have to find them explicitly. You must come up with a solution, A, B, C, D. You generate blocking clause, that's what they call it. You continue to search, and another solution is X, Y, C, D, and you have placed those values on X, Y, C, D. And let's suppose the variable order is A, B, C, D. So in other words, you have backtracked C, D, A, B, okay? D, C, B, A. And you enforce another assignment starting from X and Y, etc. So you find these two explicitly. In our approach, we identify that C, D are shared, so they're linked together. After A, B, and after X, Y, their solution subspace are the same. This is a very simple, simplistic approach because simplistic example. Because the solution subspaces that we actually share could contain millions of solutions. Okay, so we went a step further and say, well, can we, so far we say that if two search states are identical, their solution subspaces will be identical. That's no. What if two search states are very similar but not identical? Can we learn from that as well? So we call that enhancements or augmentations. So here we want to look at, again, the basic concept is if I have two search states that are the same, then the remaining subspace will be identical. Now, if they're slightly different, what can we do? So we use the notion of zero suppressed BDDs to store. Before, we store all the search states in a hash table. Now we store the search states as a ZBDD. And what is ZBDD? It was proposed in 1993 by Minato. It was proposed to represent sets. So 0 means it's not in the set. 1 means it's in the set. So you traverse from the root to any terminal 1. That means that is in the set. For example, A, B is in the set. It is a set. No A, yes C, that's also in the set. Yes A, no B, yes C, AC is also in the set. So basically any path leading to a terminal 1 and all the edges with a one edge means it's in a set. Okay, so this is a very compact way of representing sets. Yes?
One other question. Is it not true that a conflict clause for a function represents a solution space for the complement of the function?
Yes.
So I'm wondering if, like, the existing SAS solvers and the way, so what is what you're doing, not simply dualizing what the SAS solver is doing with conflict clauses? I mean, you can't think about what you're doing as actually just operating on the complement function.
Well,
or is it more complicated
okay.
than that?
Well, for example, in ZChaf and GRASP, the number of conflict clauses, conflict clauses are learned dynamically. It's not learned statically. Statically learning conflict clauses, some people have been trying to do that, but it's very difficult. The number of conflict clauses that GRASP and ZChaf generates can be in the order of millions, and that's not even complete. So if you want to learn all conflict clauses, that would be similar to our approach. I mean, to our problem. In other words, finding all conflict clauses, not just some conflict clauses. So this will be of the same complexity, finding all conflict. Yes. So that's MP. It's a Sharpie complete problem. Okay, so we're going to represent search states in ZBDDs. So we identify partially equivalent class sets or search states to see to see what benefits we can gain. So for example, before so far, if we see that SSX and SSZ, these two search states, are the same, then we can basically link them together. Okay, that's what we know so far. However, suppose we reach SSY, a state where it's different from SSX. Okay? And in particular, if we know that SSY is a subset of SSX, this is SSX, and SSY is a subset, then perhaps we can learn that underneath SSY, there definitely exists one solution, and maybe I can generate the necessary variable assignments such that I lead to the sharing. So before I must reach a state where the search state is identical, then I can do this link. Here, what we want to do is, before you even reach this, can we enforce a decision order such that you reach this equivalence early, at this time, not at this time. Okay? So we need to also generate this multiple input assignment. So graphically, what does this mean? Before I have reached this SSX, okay, here is shown as SSX. Now I've reached SSY, which here is a proper subset of SSX. Okay? Note, because it's a many-to-one function, the overlapped assignments here for SSY and SSX, the value assignments here could be different because it's a many-to-one mapping. You could have different assignments here to SSY such that you get the same values here. Okay? So we need to find these multiple inputs so that you can get to the same search state as SSX. Then in that case, here you need to find the values needed for the remaining inputs assignments so that it can lead to the same states. So the way we do it is, for example, the assignments for SSX here is 3 equal to 1, 5 equal to 0, 6 equal to 0, 2 equal to 0, 7 equal to 0. Here is 3 equal to 1. So see, the inputs it's different on 3. So the input space here could be different. But if you do a backtrack traversal and see all the inputs outside of the cone of SSY, 5 and 6, and it can be added. And that's guaranteed to lead to an SSX. It's guaranteed. So when we do that, we can lead to this faster. We can also do conflict-driven learning in a similar idea. Suppose before you're looking for all solutions, so you're searching, and all these lead to no solutions. Okay, so the search state here is SSA. We know that, okay, and we store this. We know that underneath this search state, there's no solution. Okay. Now, when we get to the space, SSB, if SSB is a superset of SSA, superset is a proper superset, then obviously in this space there will be no solution either. You don't need to explore this space completely. Once we know that this is a superset of SSA, you can stop and say, well, definitely there's no solution there. Stop, backtrack. Okay. So the idea, again, graphically, before I've reached SSA, and the variable assignments to the rest of this formula, none of them will lead to a solution. That's what we know, because it's a conflict space. Now, different assignments have led us to SSB, such that it's a superset of SSA. Now, obviously, the rest of these white area that does not exist as assignment, that will give you a solution either. Okay, so some results. Just success-driven learning only, no enhancement, no superset subsets. This is just standard SAS solver. Okay, in some, and this is a finite state machine, S5378 is a hardware sequential circuit with 174 flip-flops. Okay, so you can represent 2 to the 179, 2 to the 179 states possible. So some properties, you can find all solutions as such. It took a little bit more time, and we set our backtrack limit to 100,000. For some harder properties, we're still able to find all solutions. Was not able. Okay, 67 million solutions in 1 second. You know, after 1 minute, it still hasn't solved 1/10 of 1% of all solutions. So this is okay. Compared with the BDD, Bingo is a commercial tool. We ask our colleagues to run these experiments for us. So it's run on different machine in the company. Well, BDDs can solve it too. So this is a 174, 2 to the 174 state space. Memory storage is about the same time-wise, or it's different platforms, so it's harder. Okay. But what if the problem size is even bigger? 1,600 flip-flops, 2 to the 1,600 state space. Bingo. This is a very good solver. It couldn't even build the transition relation. It's too large. Ours, okay, we ran this for a number of properties. We just show one here, 129 million solutions. Without it, you know, less than a percent of a percent. Okay, exhausted all possible backtracks. When you use subsets and supersets, okay, no, the number of solutions could differ because these solutions are cubes, not complete assignments. The cubes, some variables are still left as don't cares. You want to maximize the solution space as much as possible. That's why there's a slight difference, because we know that the prime implicant, if you will, from the Kano map, when you draw these cubes, the minimum sum of product may not be unique. That's basically what it says. You can find a different minimum. First of all, these are not minimum. It's just different coverings. The coverings could be different. So some cases we get a speed up. Some cases where even success-driven learning have problems. And some of these are very, very big finite state machines. We're able to finish much faster because we're able to backtrack even earlier. We know that this is, a conflict space. No solution there. You reach a superset of the search state. backtrack, or vice versa for successes. And most recently, and we've been, and other research groups are also tackling, because no work has been done on image computation. Because we know these finite state machines, when you look at this in the circuit fashion, it's a many-to-one mapping, not one-to-many mapping. So pre-image inherently for SAS solver is easier. Finding all solutions to a target state or set of states. Now, image is starting from a set of states. You want to find all the reachable states. That's inherently harder.
So yeah, as far as pre-image, suppose you take pre-image computation, how does your method compare to Ken's method?
We'll show in a little bit, but we basically we didn't run these. We didn't compare. We ran them, but we didn't compare because he couldn't even finish on any of these, and we don't think he couldn't even finish on S1423. He couldn't finish. He couldn't find all solutions because of the fact that many solutions in his paper. The benchmarks he used are relatively small. He basically showed a proof of concept. He could actually do it this way. Okay, if the solutions don't overlap, I think his method works really well. But in fact, a lot of solutions overlap. So he's chopping up his solution spaces like crazy, so that he actually will result in a greater solution explosion problem. And yeah, we ran his thing on all these. He couldn't complete on even one. He could complete it on smaller. This one has 74 flip-flops. The smaller ones wouldn't show. Even like 10, 20 flip-flops, he was able to finish. And those, the results are very comparable, but it just doesn't scale. Image computation. So all these are pre-image. There's one on image, but basically we say this is a pure BDD approach. He uses a set to find the window function, and then he uses a BDD under each window. Okay, so this is inherently not a SAT-based approach, really.
I have another question.
Yeah.
But as far as the SAT solver is concerned, whether you ask it to do pre-image or post-image, but it is just an operation on formulae. Right? When you have a formula and I have to quantify something out. So I guess what you mean really by this is actually, and I'm not an expert in SAT solvers, are there heuristics that are based on the structure of the circuit that the SAT solver is using? So why is pre-image or post-image different for a SAT solver? That's my question.
Okay, next slide. Given a state here, you want to find the pre-image. See, if you make assignments here, your implication power is much greater. Your BCP, your Boolean constraint propagation. When you assign a 0 here, you can, because circuits simulate forward. There is a way to backpropagate, but when you backpropagate, the values may not be unique. For example, to get a value of 1 here, this could be 1 or this could be 1.
So what you're saying is that the SAT solver's backtracking heuristics work naturally for
Yes.
image.
So for image computation, given a starting state, you want to find all possible, basically you want to find a range. So the naive approach is you enumerate all the other unassigned variables. You enumerate all of them to see what is the set of values you obtain here. That would be the image. That would be the naive approach. However, this, again, will not scale. So basically we want to borrow, I want to skip these because it's already 11:30, some of these details. Basically, the questions we have asked is how do we pick the solution decisions, and how do we use our equivalent search states to help us learn, and then how do we minimize the image obtained. And we do this in what we call a clever, cute way, okay? Because we're trying to solve this like as if we're trying to solve a pre-image. Essentially, what we know before, given a search state, this is a decision tree, we know that if I reach another search state that is the same, we know this decision tree will be exactly the same. We know that before. So suppose you're given this is your starting state. You want to find an image here. Then I want to enumerate the rest of these unassigned variables. And when I make decisions on these unassigned variables, they lead to this decision tree. There will be corresponding search states, and maybe we can use that to help us prune the search space. So the idea is the following. Given a decision node in your decision tree, on both branches, you can have, of course, the subtrees, but also the current image obtained on those. And, for example, if the image, the next state variables assigned so far on here is x1, x2, and on this branch is y1, y2, then we can store them as a ZBDD. We store them as a ZBDD, x1, x2, no x1, y1, y2. Then if these two are the same, suppose, that's hypothetically, they're the same, then these two nodes, even these two subspaces will be the same. So we do it in a augmented fashion. This is the original Boolean formula. Okay, and we learn just like pre-image computation. You make variables here, you make decision variables here. We do it intelligently, which I'm not discussing in this presentation because I'm time limited. You pick variables intelligently. You do this, and then this is your decision tree. And this is the image tree, because at any given point in time, you have an image obtained, and any sharing of the search state in the decision tree also maps directly. We have a proof in that in our paper that the ZBDD will also be the same. The image obtained will also be the same. So this is how we do the image computation. So at the end, we have an image of the variables here. We link them together. So comparison here, we actually we compare with Macmillan's. That's a set. Macmillan's method, and this is BDD. When it's max here, it means either memory out or time out. Our time is 1800 seconds or half an hour. Okay, so it can actually be much greater than these values. So BDDs did fairly well for the smaller designs, smaller finite state machines. But once it gets bigger, this is already maxed out. Okay, for these two, maxed out. SAT or basic ATPG, or ATPG stands for automatic test pattern generator. It's like SAT. It's synonymous to SAT, but it works on a circuit instead of a generic formula. That's yellow and red. Okay, for some small ones, but it's difficult. They also maxed out. For some, it was able to finish. So see, these two, they track very much with each other because they're sort of synonymous. Okay, ours is green. It's consistently lower. Okay, for all these, and we think this has tremendous potential to symbolic traversal in large finite transition systems. In terms of number of cubes, there's a number of cubes found. Okay, again, these doesn't mean that it's 100,000. It's maxed out. It's much greater than that. This is ours. So Macmillan's method, many more solutions because you actually chop up the solution space. Basic ATPG, that's a naive. You just backtrack. Okay, so ours is much smaller. In terms of number of nodes in the final image, okay, also very compact, which is very nice. And the BDD, the BDD is our order BDD. So we know that order BDDs are generally speaking much bigger than free BDDs. That's why the number of nodes also is much greater. And again, all these are on a log scale. So it's not just, this is orders of magnitude. All these are order of magnitude in time, in number of cubes, in the number of nodes in the final representation. All these are 2 to 3 orders of magnitude improvement. So we're really excited by this work. So in conclusion, we have proposed what we call a success-driven learning, as opposed to conflict-driven learning. And that is both time and memory efficient. Because first we said, okay, we trade off time with space. But in fact, at the end, we win in both time and space, which is quite exciting. And we sort of solving the Sharpie complete problem. Finding one solution is still incomplete. I'm not saying that we solved that problem, but we're one step closer to the Sharpie complete problem. It's a seamless integration. Partial state equivalence, we talk about the supersets and subsets. We combine conflict and success-driven learning, image computation. We extended this to image computation. It's the first of its kind. that actually works. The others, they don't really scale. And then potential for significant increase in capacity of model checking, we believe, for verification. And I talked about the slide in the beginning already. And this has been funded by 2 NSF grants and also a grant from Intel. So with that, I'd like to conclude my talk, and I thank you very much for attending my talk and being more than happy to chat with you with the more details of our work and etc.
Further questions you can ask them. Michael will be here this afternoon. Send me an email.